Hello, my name is Adarsh Narayanan, and this is the video report for Lab 1 Constant Velocity. So for our introduction, the purpose of this lab is to analyze one-dimensional constant velocity motion and compare real-world data to a computational model. We do this by rolling a marker and obtaining its observed position using the tracker software and obtaining its predicted position using GlowScript. For our physics principles, this is based on Newton's second law. For constant velocity, net force equals 0, so acceleration also equals 0. Our main result, position versus time was linear, and the zero net force model closely matched the observed motion. Newton's second law, what is it? Newton's second law in momentum form states that the net force on an object equals the rate of change of its momentum over the change in time. We can derive the velocity update formula from this equation. We can move change of momentum over to the other side, and we know change of momentum is the final momentum minus the initial momentum, so we just plug that into the formula, and then we move over initial momentum, and we get this formula. We also know that momentum is mass times velocity, so we just plug in mass times velocity for momentum, and then we would divide mass out of the formula, and this is the final formula that we get. What is our lab experiment procedure? First, we want to record a video of a marker moving in a straight line at about constant speed, with the camera fixed and a meter stick visible for scale. We would then import the video into Tracker, calibrate the scale using the meter stick, and then track the object frame by frame to collect position versus time data. And then we export the data from Tracker into the spreadsheet, and then we build a computational model in the GlowScript, output model time and position data from GlowScript, and also paste it into that same spreadsheet. And then we plot both graphs, observed x versus time and model predicted x versus time on the same chart and compare. This is our Tracker software. So first, each diamond represents the center of the mass that was clicked so that we can get the position at a certain time. You can see the graph indicating that we're going linear, but in the negative axis. That is just because we were going in the opposite direction that you would usually go in. For Tracker analysis, our initial time was 0 seconds, and our final time was 3.067 seconds. Our observed position was 0.0036 meters, and then 1.007 meters. So to calculate the velocity that we want in the computational model, all we do is use the average velocity. So that is change in x over change in time. The change in position is 1.00367 meters, and the change in time is 3.067 seconds. And then we would divide the two numbers, and we get a final velocity of 0.327 meters per second. So for a computational model, using the starter code, we can change the initial position and the velocity to represent our Tracker data. So first, we changed the position to the initial position, and then we changed the velocity to the velocity we calculated in the last slide. And then we changed the net force to 0 to represent constant velocity. And mass stays unchanged because if F net equals 0, then the velocity does not change with a different mass. And then this is the graph that we obtained by using the computational data and then using the Tracker data. So as you can see, both the graphs are very similar. It's just the Tracker data is a little inconsistent in its linear form. So the data isn't exactly linear, but we can see that it is very close to what the computational data represents. So of course it wasn't the same, right? So we have some sources of error. One of them is calibration error. The ruler/meter stick may not have been perfectly aligned with the motion, causing scale inaccuracies. There could be tracking error in Tracker. Clicking slightly different points of the object frame to frame introduces small position errors. And then there could be rounding in calculations. Spreadsheet or GlowScript rounding effects slope/velocity values slightly. And then of course we got some surroundings error. So the surroundings is everything outside of the marker. So it could be a table next to you, it could be the air, it could be anything really. And the marker is the system. So air resistance and friction may affect the system, and that could give some slight inaccuracies in your data. Additional questions. So what if the positive x-axis and the negative x-axis were interchanged? Really, the only thing that would happen is the slope of the graph would be negative instead of positive. It would not affect anything in the data. Is it possible for you to say how many pushes and pulls i.e. how many forces are being added together to give net force of 0 in the case that you observed. So the number of individual forces acting together to make a net force of 0 cannot be determined with just the object's motion. However, we do know that the y direction, that the force of gravity and normal force cancel out to 0. But because the computational data and the experimental data are slightly different, we can say that there are additional forces acting on the system. Thank you for listening to my presentation.